Hello everyone. After discussing about the preparation of haloalkanes or alkyl halides, now we'll focus on the properties, that is the physical as well as the chemical properties of the so-called compound haloalkanes. Now before proceeding with the properties of alkyl halides or haloalkanes, now let's have a recap of the preparation of alkyl halides. Let's discuss all this preparation by use of some examples so that we are very much sure about how this reaction takes place and what are the possible products that could be obtained when a particular alkyl halide is to be prepared from a given substance. So coming back to this, now we have an organic compound C5H10. This is a hydrocarbon. Now these hydrocarbon reacts with chlorine in absence of light, that is dark condition, when no reaction takes place. So these hydrocarbon, fluorination in absence of light, no reaction. These hydrocarbon, same hydrocarbon C5H10 reacts with chlorine in presence of light, when this gives you only one monohalogen substituted alkane, monohalo compound. That means these hydrocarbon on the reaction with chlorine gives only one monohalogen substituted hydrocarbon. So the compound question is, what is this compound? What is the structure of this compound? Find the compound. What is this? So first of all we have to see, since only one product is formed, that means all the hydrogens are identical, means all the carbons are identical and all the hydrogens are identical. So replacement of any of this hydrogen gives you only one product, that is single product. So this indicates all the hydrogens are identical. That means these hydrogens are attached to carbon, all the carbons are identical. So look at this compound seems to be an unsaturated compound, but this on the reaction with chlorine gives only one monohalogen substituted compound. So this product clearly indicates the presence of only one type of carbon. If only one type of carbon is present, means all the hydrogens are again identical. So the compound, you have to define the compound. So look at this. This cannot be alkene. If you are having alkene, then we have different types of carbon. So the compound should be cyclic compound. So the compound is cyclopentane. So if you look at the cyclopentane, all the carbons are secondary, only one type of carbon. Since all the carbons are secondary, so all the hydrogens are secondary. Replacement of any of this secondary gives you the equal product. So this reacts with chlorine in presence of sunlight, when this gives you chlorocyclopentane. Chlorocyclopentane. 10. So this is the product. Now, similar to this type of question, I'll give you one more question. Let's take this C5H12. So we have an hydrocarbon C5H12. These reacts with chlorine in presence of sunlight. How many different types of monohalogen substituted alkanes will be formed? How many monohalo derivatives will be formed? How many different types of monohalogen derivatives will be formed? So for this, we have to consider different types of the structural isomers of these compound C5H12. So look at this. C5H12, we can have CH3, CH2, 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 CH3. Now look at this. This carbon CH3 and this carbon CH3 both are primary. So replacement of hydrogen from this primary will give you one product, because both these carbons are identical. Take this carbon, these two carbons are secondary and the nature of these secondaries are identical. So replacement of hydrogen from these secondary will give you one product. Then we are left with another carbon. This carbon is also secondary, but this secondary carbon is different from this secondary carbon. So look at this, how this is different. If you look at this secondary is attached to primary and secondary, whereas this secondary carbon is attached to secondary and secondary. So we have different types of secondary hydrogen. So whenever we have different types of secondary hydrogen, we will get different halogen substitute products. So one product will be coming from this. So these N-pentane, that is N-pentane. So N-pentane contains 3 different types of hydrogen. So this gives you 3 products. So let me see what are the products here. The products are CH2Cl, CH2, 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 CH3. That is substitution at primary carbon. Then we can have CH3, CHCl, CH2, CH2, CH3. That is substitution at secondary. That is 2-chloropentane. Then we can also have CH3, CH2, CHCl, CH2, CH3. So these are 3 different products that is formed from this and pentane. Normal pentane. Now another structural isomer possible for this compound is CH3, CH, CH3, CH2, CH3. This is 2-methyl butane. So if you look at this, these 2 carbon atoms are primary and this primary is attached to this tertiary carbon. So these 2 carbons are identical. So this replacement of any of this hydrogen will give you one product. This carbon is tertiary. Tertiary carbon has got one hydrogen. Replacement of this carbon hydrogen will give you one product. This carbon is secondary. So we have replacement of this secondary hydrogen will give you one product. Then we have this primary. This primary carbon is different from this primary. The reason being, this primary is attached to secondary carbon, whereas this primary is bonded to tertiary carbon. So we have different types of primary. So from this primary we get one product. tertiary one product, secondary one product, and this gives you one product. So total how many products will be formed? 4 products will be formed. And let's see what are the products here. CH2Cl, CH, CH3, CH2, CH3. Substitution at this primary. Then we have substitution at tertiary. CH2, CH2, CH3. Substitution at secondary carbon. Cl, CH3, then CH3, CH, CH3, CH2, CH2, Cl. If you look at it, these are all structural isomers that has been formed. So this compound, if this gives you 4 products, then the structure will be 2-methyl butane. Then look at this. Third possibility is we have this CH3, C, CH3, 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 that is neopentane, 2,2-dimethyl propane. If you look at this carbon is quaternary carbon, and all the remaining carbons are attached to this quaternary carbon, and all these are primary. So these 4 primary carbons are identical. So replacement of any of this hydrogen will give you only one product. So these particular compounds C5H12 on chlorination, if question says only one monochloro compound is formed, then the structure will be neopentane. So this gives you only one product, CH3, C, CH2Cl, CH3 and CH3. So this C5H12 chlorination gives you 3 product, monohalogen substrate product. This is the structure N-pentane. If this gives you 4 product, this is 2-methyl butane. If this gives you only one product, then this is neopentane. So this is how we derive the structure from the number of monohalogen derivatives, or from the given structure we can derive how many monohalogen derivatives will be formed. Take this reaction. Another example, we have benzene, CH double bond, CH2. Now these reacts with HBr. We have alkene, alkenes react with HBr, so this is Markovnikov addition, electrophilic addition. So according to Markovnikov addition, negative part of the reagent goes to that carbon atom having less number of hydrogen, positive part goes to that carbon having more number of hydrogen. The reason being formation of classical more stable carbocation. So we have this CH, CH3. Now take the same alkene. Now this reacts with HBr in presence of peroxide. So in presence of peroxide, we will have peroxide effect or Kharash effect, or which is known as anti-Markovnikov addition. Now peroxide effect, anti-Markovnikov. So the product will be just opposite of the Markovnikov addition. So the product will be CH2, CH2Br. So this is peroxide effect, that is anti-Markovnikov addition, or Kharash effect, that is Markovnikov addition. Take this CH3, CH2, CH double bond CH2. This reacts with NaBr plus H2SO4. So NaBr first react with H2SO4 when this gives you HBr. So this is nothing but addition of HBr to this alkene. Again the reaction will be Markovnikov's addition, CH3, CH2, CH, Br, CH3. Now take this alkene, react with this HI in presence of peroxide. Now addition of HI in presence of peroxide, again reaction will follow Markovnikov's addition, because as I told you, anti-Markovnikov is only with this HBr in presence of peroxide. Remaining hydrohalic acids will not show peroxide effect. So still we have the product, that is CH3, CH2, CHI and CH3. Then we have look at this reaction, CH3, CH2, CH2OH. Now this reacts with Cl2 in presence of red phosphorus. This reacts with PCl5. This reacts with SOCl2. Now this alcohol reacts with Cl2P, means these two combines to give you PCl3 and PCl3 reacts with this. So this gives you normal product CH2, CH2Cl, plus the side product will be H3PO3. Alcohol plus PCl5, same product CH2, but the side product will be POCl3 plus HCl. With SOCl2, as I told you, this is one of the best methods for preparation of alkyl chloride. The reason being the side products are gases. CH3, CH2, CH2, Cl plus sulfur dioxide case plus HCl case. So no further purification is required. So these were some of the methods that we have discussed for preparation of haloalkanes from different compounds. So this was just a recap for those methods of preparation that we have discussed. Now coming to the properties of this haloalkanes. Now coming to the properties. Properties of these halogens. So for this, first let's take up this physical properties. Physical properties of halogen derivatives. Now, first of all, let's discuss nature of carbon halogen bond. Nature of carbon halogen bond. Now if you look at this, we have this carbon, this is halogen, this halogen may be fluorine, chlorine, bromine or iodine. Now we all know halogens are more electronegative than the carbon. So since halogen being more electronegative, the shear pair of electron is shifted more towards halogen. As the electron pair is shifted on halogen, electron density on halogen increases. So this halogen will acquire partial negative charge. Now electron is moving away from carbon. So electron density on carbon decreases. So this carbon will acquire partial positive charge. To simply saying, all carbon halogen bonds are polarized covalent bond due to the electronegativity difference. So the bond is polar covalent due to the electronegativity difference. So we have this polarity. Now polarity present in the compound is measured by a physical quantity known as dipole moment. So bond is polar covalent due to electronegativity difference. So we have an electronegativity difference. Because of this, bond is polarized. We have a dipole, positive pole and the negative pole. So we measure this by dipole moment. So let's discuss dipole moment. So before this dipole moment, let's discuss bond length. Bond length. So we have looked at this CF, CCl, CBr, carbon, iodine. Now carbon remains same. The only difference is halogens. So moving from fluorine to iodine, size of halogen increases or electronegativity decreases. As the size of halogen increases, the effectiveness of bond decreases. As the effectiveness of overlapping of orbitals decreases, the bond length will increase as the atomic number of halogens increases. So this is due to increase in size of halogens. So as the size of halogen increases, bond overlapping of atomic orbitals decreases, bond length increases. Now as the bond length increases, bond strength will decrease. Bond strength, this CF is the strongest bond, followed by CCl, followed by CBr, followed by CI. So this is the bond strength. Now number 3, dipole moment. Dipole moment, that is the polarity present in the compound. Now we all know this dipole moment is a vector quantity which depends on the charge carried by the dipole and the distance between the dipole. So exact value of this dipole moment will be defined by this product of these two terms. E represents charge on the dipole, D is the distance between the dipole or simply the bond length. E, charge carried by the dipole, and this D is the distance between the dipole, or distance is nothing but the bond length. So to define dipole moment, we have to consider this product of these two quantities, charge and distance between the dipole. Now look at this. We have discussed that CX bond is polarized covalent bond. Now maximum polarization will be possible in case of CF, because fluorine being the most electronegative atom, polarization of this bond will be maximum. That means the charge carried by the dipole will be maximum in case of CF, minimum in case of CI. Now as the charge separation between C and F being the maximum, the ionic character of CF will also be maximum. As the ionic character is maximum, bond strength will become much more, or bond becomes much shorter. So considering these two, E and D, the dipole moment of these compounds, that is, when we consider this look at this, CH3Cl, means we are considering this dipole moment. So chloromethane will have higher dipole than fluoromethane, followed by CH3Br, CH3I. So please make sure this point. Charge separation is maximum in case of CF, but due to maximum charge separation, bond becomes much shorter, so the overall product, this quantity is more, but this quantity becomes very small, so the product of E and D is slightly greater with chloromethane than CH3. If E is less, but the distance becomes more. In the first case, D is more, so the product of E and D is more. To methyl chloride is having greater dipole than CH3F. Similarly, we can also consider some other examples like look at this CH3 Cl CH2 Cl2 CHCl3 CCl4 chloromethanes, chloromethane, dichloromethane, trichloro or chloroform carbon tetrachloride. So for these chloromethanes, the dipole moment order is this way. Carbon tetrachloride dipole moment is 0, maximum dipole is with is CH2Cl. So we have to consider the tetrahedral structure, then we have to find out the overall vector product, resultant vector of all the dipoles present. Let's take some other examples of this dipole moment. Take this, we have this chlorohexyclohexane and this chlorobenzene. Cyclohexyl chloride and chlorobenzene. Now, the dipole moment of this cyclohexyl chloride is greater than chlorobenzene. Now, we have to explain this. So, in this cyclohexyl chloride, this is chlorobenzene. So the dipole moment of cyclohexyl chloride is greater than dipole moment of chlorobenzene. We have to explain. Now for this, look at this. Chlorine is same. So electronegativity of chlorine remains same. Now we have two different carbons here. This carbon is sp3, whereas benzene carbon is sp2. Now moving from cyclohexyl carbon to benzene carbon, hybridization changes from sp3 to sp2. Now the percentage of S character is more in case of sp2 than sp3. As the percentage of S character in the hybridization increases, electronegativity also increases. So benzene carbon being sp2 is more electronegative than cyclohexyl carbon, which is sp3. As the electronegativity of carbon increases, electronegativity difference between carbon and chlorine decreases. Means the polarization of CCl bond decreases. Now along with this polarization of CCl bond decreases, the resultant vector, that is E into D factor, is more for this cyclohexyl chloride than chlorobenzene. So I hope you got the point. This is due to difference in the electronegativity of carbon bearing halogen. Chlorobenzene, carbon is sp2, more electronegative, so electronegativity difference is less or less polarization of CCl bond. So polarization is more in case of cyclohexyl chloride, hence the dipole moment of cyclohexyl chloride is greater than the chlorobenzene. So this is the dipole moment of halogen substituted alkanes. Then we have boiling point. boiling point of halogen substituted alkanes. Now boiling point depends on the intermolecular attractive force between the molecules. So these molecules have van der Waals force of attraction. So stronger the van der Waals force of attraction between the molecules, boiling point will be more. If the van der Waals attractive force is less, then the boiling point will also be less. So this strength of van der Waals attractive force depends on the size or the surface area. So if the surface area of the molecule is more, the strength of van der Waals force will be more. If the surface area is less, the strength of van der Waals force will also be less. And this surface area also depends on the size. If the size is more, surface area is more, then the attractive force will be more. So look at this, boiling point is proportional to the strength of van der Waals attractive force, and this strength of van der Waals force, this van der Waals force depends on surface area, and this surface area depends on the size. To simply saying, as the size increases, surface area increases. As the surface area increases, the strength of van der Waals force increases. Hence, the boiling point will also increase. Now, with increase in branching, अगर branching शुरू करेंगे तो surface area decreases, because with increase in branching, molecules assume spherical in nature. So as the surface area decreases, the strength of van der Waals force decreases, boiling point will decrease. So linear chain compounds will always have more boiling point than the branch chain isomers. Take this case. So this is normal chain halogen, that is 1-chloropentane take this 1 2 3 4 5 1 2 3 4 5. So these are with these formulas C5H11Cl. Number of carbons remains same, number of hydrogen remains same, number of Cl remains same. The only difference is branching in the chain. Now with increase in branching, now look at, this is not a branch, this is normal chain. We have a branching here, we have a branching. As the branching increases, surface area decreases. As the surface area decreases, the strength of van der Waals force decreases, the boiling point also decreases. So when we compare the boiling point of normal chain is greater than this, then this is less than this. This is the least because of this. With branching, surface area decreases. So as the surface area decreases, van der Waals attractive force also decreases. So the boiling point decreases. So when we compare isomeric compounds, branch chain isomer will always have lower boiling point than straight chain isomer. This is the reason. Now take this case CH3F, CH3Cl, CH3Br, CH3I. So we have these chloromethanes. These chloromethanes, we have to consider their boiling point. Now look at this, moving from fluorine to chlorine to bromine to iodine, the size of halogen increases. As the size of halogen increases, surface area of molecule increases. As the surface area increases, the strength of van der Waals attractive force increases. Hence, boiling point also increases. Due to increase in size of halogen, surface area increases, strength of van der Waals force also increases. So let's compare some other examples also. The CH3Cl, CH3Br, CH2Br2, CSBr3. So let's take these compounds. Now look at this, moving from chlorine to bromine, size of halogen increases, surface area increases. We have one bromine, we have two bromine. Obviously size of two bromine is greater than size of one bromine. So again surface area increases. As the surface area increases, strength of van der Waals force is increases and the boiling point also increases. Let's take up some more examples. Similar to this, CH3Cl, CH2Cl2, CaCl3 and CCl4. Now look at this, moving from chlorine 1 to 2, 2 to 3, 3 to 4, surface area, obviously size increases, surface area increases, so the strength of van der Waals force increases, the boiling point also increases in this way. So I'm just giving you some comparative values how we can compare the boiling points of various compounds. Take this, CH3, CH3, Cl, CH3, CH2, CH2Cl, we have this. This is isopropyl chloride, N-propyl chloride. Now obviously look at this, this is a linear chain, this is branch chain. Carbon number is same, hydrogen same, Cl same. The only difference is branching here, no branching here. So unbranched chain will have more surface area, more van der Waals attractive force, so this boiling point will be greater than isopropyl chloride. But this and this, no doubt we have a branching here, but the number of carbon also increases. So we have, this is propyl, this is pentyl chloride. So obviously as the number of carbon increases, size will also increases. As the size increases, strength of van der Waals also increases. So this is how we compare the boiling point of various halogen substituted alkyl halides. So this is comparative study of boiling points. So keep in mind, boiling point depends on surface area, more is the, depends on van der Waals attractive force, and van der Waals attractive force depends on surface area depends on the size of halogen or the compound. Next is density. Now lower halides like fluorine and chlorine substitutes are generally less denser than water. So when we compare the density of halides, Ri, look at this, as the size of halogen increases or as the mass of halogen increases, density also increases. So Ri is greater than Rbr. So RBr density is greater than water, and water has been having more density than RCl. RCl is having more density than RF. So density of bromides and iodides are greater than that of water, and the density of water is greater than that of chlorides and fluorides. So similarly we can consider, look at this, CCl4, CaCl3, CH2, Cl2. Density of CCl4 is greater than CaCl3, which is greater than CH2Cl2. This is greater than the density of water, and density of water is greater than CH3Cl. So this is how we compare density of these halogen substituted alkanes. Next is we have solubility. Now halogen substituted alkanes, alkyl, though now there is a polarization in the molecule, but we know that the polarization is not very strong. So these are weakly polarized covalent compounds. Because of these being weakly polarized, these compounds are very less soluble in polar solvents like water. So these are having very poor solubility in water, but these have very strong solubility in organ solvents. Now we have to explain why these halogen substitute alkanes or haloalkanes are very poorly soluble in water. Soluble in water. So we have to explain why. Now we know, not that we know that solubility is less, but why these are less soluble? Why these are not very soluble in water? Now look at this. We have looked at this water molecule H2O. Between this water molecule we have hydrogen bond. So the attractive force between water molecule is hydrogen bond. So hydrogen water molecules are associated through hydrogen bond. Now we have this Rx and this Rx. Now in between these two Rx, this attractive force, this is van der Waals force. So between Rx and Rx we have van der Waals force. Between water and water we have hydrogen bond. So the strength of hydrogen bond is always greater than the strength of van der Waals force. So when we mix these Rx in water, the attractive force between alkyl halide and water molecule is not large enough to overcome the stronger hydrogen bond. So because of this, since Rx molecule, the attractive force between Rx and water molecule is weak compared to this hydrogen bond, so this energy release cannot break the stronger hydrogen bond that is being present between water molecules. As a result of this weak attractive force between alkyl halide and water, these two cannot be mixed, or this is not soluble in water. I hope you got this point. Let me explain again. In alkyl halide, the attractive force is weak van der Waals force. In water molecules, the attractive force is through hydrogen bond. The strength of hydrogen bond is greater than strength of van der Waals force. So when we mix this alkyl halide in water, the attractive force between alkyl halide and water is not strong enough to overcome this stronger hydrogen bond present between the water molecules. Since These RX molecules cannot break this hydrogen bond present between the water molecules. The solubility of this RX in water is less. That means we say the weaker force of attraction between water and RX is not sufficient to break that stronger hydrogen bond present between water molecules. Hence, their solubility is less. So, this is about solubility. So, simply saying these molecules are less soluble in water. The reason being the bond is the attractive force between alkaline and water cannot break the stronger hydrogen bond present between the water molecules. So, this is the explanation. Now, these are some of the physical properties. Apart from these physical properties, let's come to some chemical properties. Some chemical properties. First, tell the chemical properties mean formation of organometallic compound. Formation of organometallic compounds. So we have a term organometallic. Organo stands for carbon compound. Metal means metal. So reaction between highly electropositive metals and the organic compound resulting in the formation of a specific bond known as organometallic bond. So let's look at this. We have this RX. RX reacts with magnesium metal in presence of dry ether. So look at this, I am using a specific solvent, that is dry ether. When this gives you RMgX, this is alkyl magnesium halide. These alkyl magnesium halides are commonly known as Grignard reagent. Grignard reagent in honor of the scientist Grignard, for whose discovery he was awarded Nobel Prize. So this is one of the most versatile reagent that is used in organic chemistry, because this is very reactive and many organic compounds, functional groups can be prepared from this organometallic. This is alkyl magnesium halide, that is Grignard reagent. Now let me explain the nature of bonding in this alkyl magnesium. So we have R, Mg and X. Magnesium and halogen. The bond between magnesium and halogen, this bond is ionic. It is ionic bond. So we have magnesium plus and Cl X minus. So bond between magnesium and halogen is purely ionic. Now we have this bond between carbon of organic compound and magnesium. This carbon magnesium bond is a polarized covalent bond. So RMgX bond, R or Mg bond is polar covalent bond, and this Mgx is purely ionic bond. So in this, look at this, Mg being electropositive, it will acquire partial positive, this will acquire partial negative. So look at this, in RMgX there are two types of bond: ionic bond between magnesium and halogen, polar covalent bond between carbon and magnesium. Magnesium is electropositive, this is possibly polarized, carbon is electronegative, so this acquires partial negative. Now carbon with negative end, this carbon with negative, this can act as a nucleophile, this can also act as a base. So when carbon with negative charge is a much stronger base, so given any chance, if the solution contains any acidic hydrogen, immediately this will be destroyed. So this is the reason why preparation of magnesium halide, that is alkyl magnesium halide, is always carried out in dry ether. So these being a very strong base, solution should not contain any acidic hydrogen. If any acidic hydrogen is present, this compound is immediately destroyed. So this cannot exist. So this is the reason why we require dry ether medium for preparation. I hope this is point. So alkyl magnesium halide Grignard reagent is stable only in dry ether. In presence of acidic hydrogen, this is destroyed. So this is the reason why we are using dry ethereal medium. So this is organometallic compound. Now for this reactivity order of halogen, of Rx, Ri is the most reactive, followed by Rbr, followed by Rcl, followed by Rf. This is the reactivity order of alkyl halides for formation of Grignard reagent. Now as I told you, these being very strongly basic decompose in presence of acidic hydrogen. Look at this, RNGX. If this contains water, this decompose to give alkane plus NGOX S. If this contains alcohols also, no doubt alcohols are very weakly acidic, but in presence of this R minus, this becomes a strong acidic compound, so this gives you RH. We know that ammonia is a very good base, but in presence of this R minus, ammonia acts as an acid. So again this is destroyed. Look at this, we all know that this acetylene, the hydrogen attached to sp carbon is very weakly acidic. So in presence of R minus, again this is a very strong acid. So this gives you RH plus Ng CH triple bond C minus X. So this is the reason why during preparation of Grignard reagent, acidic hydrogens should be excluded. For this we require dry ethereal medium. Now this is alkyl magnesium. Similarly we can also prepare alkyl lithium. That is Rx reacts with lithium metal, again in presence of dry ether, when this gives you RLI, alkyl lithium. So this is again organometallic compound. So again look at this, lithium is electropositive, carbon is electronegative. So in all organometallic compounds, the carbon will acquire partial negative charge. Bone is polar covalent bond. This alkyl lithium be more electropositive than metals. Alkyl lithiums are much more reactive than magnesium. Similarly, we can have alkyl cadmium, we can have alkyl zinc, etc. etc. So this is formation of organometallic compounds. Now after this, next we go to reduction of alkyl halide by use of different reagents. First we'll take up reduction with zinc metal. Reduction of alkyl with zinc metal. So we have this alkyl halide. This alkyl halide reacts with zinc metal. So we can have different reagents. Zinc metal in presence of HCl, or zinc in presence of acetic acid, or we can have zinc in presence of ethanol. So these are the possible reagents that could be used when this reacts. We can also have look at this zinc copper in presence of ethanol. We can also have sodium amalgam in presence of ethanol. So these are a various choice of reagents. When we reduce this alkyl halide with zinc HCl, zinc acetic acid, or zinc ethanol or zinc copper ethanol, we get simply alkanes. So all alkyl halides can be reduced to alkane by use of this zinc method. So let's take this example. So we have CH3CH2I reacts with zinc acetic acid. When this gives you CH3 plus ZnI2, etc. We can have a look at this CH3, CH2, CHI, CHBr, CH3. We can have zinc HCl. When this gives you CH3, CH2, CH2, CH3, etc. So it means all haloalkanes can be reduced to corresponding alkane by reduction with zinc method. So this is reduction with zinc method. Second, reduction with reducing agent. So in this reducing agent, we'll take up different reducing agent by use of lithium, aluminium, hydride. So reduction using lithium, aluminium hydride. So look at this RX reacts with lithium, aluminium hydride. So one molecule of lithium, aluminium hydride will react with 4 moles of alkyl halide to give you 4 moles of alkane plus 1 mole of lithium halide plus 1 mole of AlX3. So okay, look at this. All alkyl halides will be reduced to corresponding alkane by use of lithium aluminium hydride. But the condition being, if the reactivity order says primary is the most reactive, followed by secondary, followed by tertiary. Primary will give you alkane, secondary will give you alkane plus alkene, tertiary will give you alkene as a measure product. So this is the meaning of primary being the most reactive. So if we want to prepare reduce alkyl halide to corresponding alkane, the best choice of alkyl halide should be primary if we are using lithium aluminium hydride. So with secondary along with this alkene product formation also takes place, so the percentage of alkene product decreases. With tertiary, major product goes in favor of alkene. So this we have to keep in mind while using lithium aluminium hydride as a reducing agent. Now, second, using sodium borohydride NaBH4 as a reducing agent. Again, look at this. We have this RX reacts with sodium borohydride. 1 mole of sodium borohydride will consume 4 moles of alkyl halide, and this gives you 4 moles of alkane, 1 mole of sodium halide, and 1 mole of BX3. Again, for this, the reactivity order of alkyl halide is tertiary is the most reactive, followed by secondary, followed by primary. Primary, no reaction takes place with sodium borohydride. Secondary and tertiary, this gives you alkane. So look at this, both are in opposite trend. Using lithium aluminium hydride, primary gives the maximum yield, tertiary gives you the least. Sodium borohydride, primary does not show any product, secondary, tertiary gives you product, and maximum product is given by tertiary. And the third reducing agent is tin halide, triphenyl tin hydride, triphenyl tin hydride as a reducing agent. So we have RX PX3 SNH gives you RH plus PH3 SNX, triphenyl tin halide. So 1 mole reacts with 1 mole 2 kb product, and the location is the best choice for reducing alkyl halide to corresponding alkane is tin hydride, because this reaction is given by primary, secondary and tertiary. So primary, secondary and tertiary gives you alkane. Sodium borohydride, tertiary gives you alkane. Lithium aluminum hydride, primary gives you alkane. So these are the choice of reagent for conversion of alkyl halides to corresponding alkane. Now the difference of this is based on the difference in the reactivity of lithium aluminum hydride, sodium borohydride and tin hydride. Now the polarity difference is maximum in case of aluminum and hydrogen. So as the electronegativity difference is maximum in case of lithium hydrogen, look at this, electronegativity difference ALH is greater than TH, which is greater than. So this being having the most electronegativity difference, this becomes much more reactive. So we have H minus sign, hydride and becomes a strong base, so this gives you alkene character. Whereas this being the least electronegativity difference, this H minus character is less, so this cannot give product with primary. This is in between aluminum and boron hydride, so this can easily react with primary, secondary as well as tertiary. So let me give you some examples of this. So this is 3 reagent. I'll combine these 3 reagent in different examples. So I'll rub this. So we have this CH3, CH2, CHI. This reacts with sodium borohydride. This reacts with triphenyl tin hydride. This reacts with lithium aluminum hydride. This is primary alkyl halide. Now look at this. Primary alkyl halide, sodium borohydride, no reaction takes place. Primary lithium aluminum hydride, so I will be replaced by hydrogen, so we have CH3, CH2 and CH2. So this is product formation. So this is reduced to alkane. This is primary tin hydride, so tin hydride reduces primary, secondary as well as tertiary. So we have CH3, CH2 and CH3. Take this CH3, CH3, CH3. Suppose this is Br. If you look at it, this is tertiary. Now we'll reduce with sodium borohydride. Will react with lithium aluminum hydride, and we also react with triphenyl tin hydride. So tertiary will be easily reduced by boron hydride when this Br will be replaced by hydrogen. So we have this CH3, CH, CH3, CH3. Now this being tertiary will be easily reduced by tin hydride. Again, this gives you the product CH3, CH, CH3, CH3. Now this is tertiary. Tertiary on reduction or reaction with lithium aluminum hydride gives you alkene. So the major product will be CH2 double bond C, CH3, CH3. Elimination takes place from this or from this or from this to give you alkene. So this is the difference between these three reducing agents. So while using this reducing agent, we have to be very specific and very careful while writing the products. So I hope with this example we can easily differentiate between the reactivity order of these three. Okay, we'll take up one or two reactions again. Number 3, that is a reaction with sodium metal. A reaction of alkyl halides with sodium metal, and this reaction is known as wurtz reaction, and the details of which we have learned in preparation of hydrocarbons. So wurtz reaction, this is a name reaction. So look at this. We have 2 moles of alkyl halide react with 2 moles of sodium in presence of dry ether. Again, look at this. Reagent is to be used in ethereal medium. When this gives you 1 mole of alkane and 2 moles of NX, this is alkane. So if you look at this, there is increase in number of carbon. If you look at this alkane, look at this, D by this. This is coming from this alkyl group. This is also coming from this alkyl group. So since number of alkyl group is 2, so there is always increase in number of carbon atoms. So we say this is alkane is symmetrical, means having even number of carbon atoms. So this is a very good method for preparation of symmetrical alkanes, alkanes having even number of carbon atoms. So we can write down this specific Rx plus 2Na plus Xr. So remove this sodium halide, and join this by RR by this single bond. The example, look at this. CH3 Cl2 reacts with sodium in presence of dry ether. When this gives you CH3 CH3. So methane cannot be prepared by use of this reaction. If you look at this CH3 CH2Cl, sodium dry ether, we have 2, this is R group, this is your R, so RR CH3 CH2 CH2 CH3. So we have, look at this is R, this is R. So it's very easy to write this reaction. So look at this, CH3 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 I. So we have 2 molecules here, sodium dry ether. So look at this part is your R. So we have the CH3 CH3. So we have RR. So if you have to find the alkyl halide from the product by this reaction, just break the molecule in 2 equal halves and break this and join this by halogen. Halogen, you will get this. Remaining, you will get the cyclotest sodium halide. So this is wurtz reaction. But if this, in this reaction, if 2 different alkyl halides are used, if 2 different alkyl halides are used, a mixture of alkanes are formed. Take this example. So we have Rx plus R prime X with sodium triether. So Rx may combine with Rx to give you R. R prime may combine with R prime to give you this second alkane, or R may react with R prime to give you this. So these are the three products that is possible. So if in case of formation of mixture of products, reaction is not feasible, but from preparation point of view, we don't carry out this mixture of alkyl halide. Just for preparation of symmetrical alkane, we use these two identical alkyl halides. Take this example: CH3I plus CH3 CH2I. This is R, this is R prime. React with sodium in presence of triether. So RR, we have CH3, that is RR. That is R prime. So we have CH3, CH2, CH3, that is R prime, R prime. We can have R or R prime plus CH3, CH2, CH3. This is R prime, this is R. So we can always get a mixture of products. This is Wurtz reaction. Then we have this Wurtz fittig reaction. This is a reaction of alkyl halide, aryl halide. So we have Rx, this reacts with aryl halide, means halogen substituted benzene, again in presence of sodium triether. So there is a coupling reaction between alkyl and aryl to give you alkyl substituted benzene. This is Wurtz fittig reaction. So reaction between alkyl group and aryl group. Then we have one more reaction, and Wurtz reaction, Wurtz fittig reaction. Then let's take this next reaction. That is Corey-House synthesis. This is a named reaction which is used for preparation of alkane. So by this method, both symmetrical and unsymmetrical alkanes can be prepared. Means whether the carbon alkane contains even number of carbon atom or odd number of carbon atom, we get both. So it's a very good or convenient method for preparation of symmetrical or unsymmetrical. Now let me give you these steps involved. So as we have looked at this, we have Rx. These Rx may be primary, may be secondary, may be tertiary. You can use any of this alkyl halide. Now this reacts with lithium metal in presence of dry ether. So there is a formation of organometallic compound, that is RLI, alkyl lithium plus LiX. The second step of this reaction, RLI, alkyl lithium, reacts with CuX, copper plus 1 cuprous halide. Sometimes this is written as Cu2X2, both are same. When this gives you R2CuLi, lithium dialkyl cuprate. This is a very important reagent. This reagent is known as Gilman reagent. Gilman reagent, dialkyl lithium cuprate. In the third step of this reaction, this R2CuLi reacts with R prime X. These R prime and R may be same or may be different. When a coupling reaction takes place between R prime and R to give you R prime plus CuX plus LiX. So this is, so if you look at this, If R and R prime contains even number of carbon, then product will be even. If R is odd number carbon, R prime is also odd number, and the product will be even. If R is odd, R prime is even, the product is odd. If R is odd, R prime is even, then also odd. So both you can use. Let me give you one or two examples here. So one thing you have to keep in mind, this alkyl halide R prime should always be primary. If you take secondary or tertiary, product will be alkene. So don't forget to use this alkyl and alkyl halide. Take this, we have CH3Cl reacts with lithium in dry ether. So this gives you CH3Li. And second, CH3Li reacts with CuCl to give you CH3 whole twice Culi, that is R2CuLi. Third, CH3 whole twice CuLi reacts with CH3 CH2 Cl. Okay, this is R prime X. This is R prime. So the product is, this is R CH3 CH2 CH3. This is the product. So look at this. This contains odd, this contains even, so the product is even. So this is how we modify this preparation of alkanes by use of this medium. One more example, CH3CH2Cl. First, this reacts with lithium in presence of dry ether. Second, Cu2Cl2. Third, CH3CH2CH2Cl. So this is R, this is R prime. So the product is just coupling between R and R prime. So the product will be CH3 CH2. This is R. R prime is CH2 CH2 CH3. This is R prime. So even plus odd, compound is odd. So these are some of the few important, chemical properties. We'll continue with the chemical properties, extensive chemical properties in next video series. Hopefully you enjoy this class. Bye bye.